Okay, so let's address this issue of the proliferation of parameters. Okay, these Wn, there are n parameters corresponding to the bump height, which is going to lead to overfitting because we are guaranteed to fit the data, and if there's stochastic or deterministic noise, we're going to fit the noise and be led astray. Okay, now, basically, if we want to reduce the number of parameters and each parameter corresponds to a bump height, we have to reduce the number of bumps. Okay, so let me show you in 2 dimensions for a change what's going on. Okay, so, I'm going to draw some data points, and you'll get the picture. You'll figure out very quickly what's going on here. Okay, so I have a bunch of data points, and now I'm going to place a bump on each data point of a particular height, and then the bump on a data point and its height tells me how much it affects a test point x. Okay, and if the test point is far from the bump, then it's going to affect it less, and if the height of the bump is larger, then it's going to affect it more. Okay, but now I'm going to put a bump on each of these points, and I don't need a bump on all these points because all those bumps effectively combine to one bump. Okay, but having separate bumps gives me separate parameters which I can fit to the data and hence overfit. Okay, so the idea in reducing the number of bumps is to sort of be motivated by this kind of data and say, you know what, I really just need one bump to represent that set of data. And, a typical test point will either be close to that set of data or not. Okay, and it shouldn't be a big deal, that it's specifically this close to that point and that point and that point, and each of these points gets their own bump and their own parameter to affect a test point. Okay, so basically what we're suggesting is that look for data that's close to each other and aggregate the effect of all of that data into one bump. Okay, and where's that bump going to be located? At some center that's representative of that data. And similarly, we will locate another bump at some center representative of some other data somewhere else, and a bump here, and a bump here. And you see that what we have done is sort of identified the centers of the clusters of the data as the right places to place the bumps. Now, of course, we could put a bump on every data point, but it's overkill when the data is clustered in this nice tight way. So in this example, we see that we only need 4 bumps, even if we had 1,000,000 data points. Okay, so in this example, we only need 4 bumps. Okay, and so that's the idea behind how we're going to reduce the number of parameters. We're going to say, well, we don't need n bumps, 1 on each data point. Let's decide on a number of bumps. So number of bumps, k. Okay, and for each bump, we have to specify its center. Okay, with centers mu1, mu2, mu3, up to mu k. Okay, so just now previously we had n bumps, okay, and those n bumps were placed at the centers which corresponded to the data points. Now I'm allowing the centers of the bump, well, they might be data points, but they don't have to be. Generically speaking, allowing the bumps to centers to move around in order that they can represent well the data. Okay, so the bump centers in some sense cover the data. Okay. Now let's think of a typical data set. So the bumps have centers. Okay, so there are k bumps, and the centers are placed somewhere, and they'll also have a radius, and we'll talk about the radius in a while. Okay, but the point is that once I've identified the centers, I have my feature transform. So my feature transform takes x, okay, to a z, which is phi. So how similar is x to my first bump center, phi of x minus mu1 over r, phi. So the second feature is phi of x minus mu2 over r, and so on, phi of x minus mu k over r. So now, whereas before I had n similarity features, one similarity for any input x to each of my data points, now I have only k similarity features, a similarity from my input to each of my k bump centers. Okay? And now I have the standard linear model. Okay, so the standard linear model. Okay, g of x. Okay, now I'm here in the parametric RBF where I'm allowing a bump on every data point. Okay, I don't really need a constant because I can guarantee fitting the data. But now, if the data has a certain bias, then we should allow for that bias. Think of that as the augmented one. So we're now really doing the linear model. Okay, so we're going to have the augmented one. So my final hypothesis is W0 plus the sum from j equals 1 to k wj phi of x minus mu j over r. Okay, so that's the linear model that corresponds to this feature, and we can write this as W0. Well, we can write this as W transpose Z, where I now imagine that in my feature vector I also have the augmented one. So I also add the augmented one to my feature vector. And now I have exactly a linear model, okay, where my features are similarity features to my k bump centers. And okay, the augmented one. And this is a perfectly valid linear model, providing that I have specified the bump centers. Okay. But now an interesting possibility arises that I have parameters which are the weights and also parameters which are the bump centers. And in principle, I can vary both the weights and the bump centers in order to fit the data. Okay. So this particular model, this part of the model, this is a nonlinearity. So this particular final hypothesis is non-linear in the mu sub j. Okay. So if I wanted to explore the full flexibility of this model, I would have my linear weights and my nonlinearity in the bump centers. So this is the first example of a model that we're studying that's actually, explicitly nonlinear. Now, the interpretation of these nonlinear, this nonlinearity is that you get to choose centers in your data. You get to choose prototypes. So you can choose your prototype that sort of represent the data well. Okay? You can choose prototypes that represent the data well, which means that you're engineering, you're tailoring the features, the similarity features to the data. Okay? And that interpretation is going to allow us to actually give you a very good and very efficient algorithm for selecting the bump centers. And so let's have a look at that algorithm for selecting the bump centers, because after you have selected the bump centers is just a linear model. Okay, so after selecting bump centers mu j, it's a linear model. You have a linear model. Okay. Okay. So let's investigate a little bit this model and then see some results. Okay, so let me summarize the model here, and we'll also summarize it in a picture. Okay. So summary. And this model is called the parametric radial basis function network. So parametric radial basis function network. Okay. And there's a nice visual that goes along with this, which I'll show you. Okay, which is to sort of visually represent this as a network, and it'll be a helpful visualization when we connect to neural networks later. Okay, but the basic idea is, in going from the parametric RBF to the parametric RBF network, is to reduce the number of bumps. Reduce bumps. Okay, and so my final hypothesis G of x is equal to my augmented W0 plus, okay, the sum from j equals 1. So the sum of bumps, sum over bumps, okay, of Wj, my weights. Okay, now here comes the interesting part. My similarity feature for my test input x with my prototype, my bump center, j. So this is a similarity feature. Okay, and then I just take the weighted sum of the similarity features, add my bias term, okay, and I've got my output. And if I'm doing classification, I take the sign of this. If I'm doing logistic regression, I'm going to have to, I'm going to use this as the probability of y given x, okay, and I'm going to minimize the cross entropy error, okay, with respect to y value. So, okay, and we'll see how that's going to happen. So I'm going to ultimately now want to reduce this to a linear model. The problem is it's currently nonlinear because of these nonlinearities that are present, because we have to set the bump centers, which we're also going to do using the data. Okay. But let me give you a helpful visual. So what's going on here? So you have your input x. Okay. And you transform your input x, okay, using, the similarity to the center mu j. So x, okay, so x minus mu1 over r, x minus mu2 over r, and so on, x minus mu k over r. Okay, so you sort of transform x by computing its similarity to the centers, to each center, pass it through your kernel function, okay, similar to passing the linear signal to the sine or the sigmoid. So you pass it through your kernel function, and then you have your augmented one, and you now implement a linear model. W0, W1, W2, Wk. So you multiply by linear weights, and you output, g of x. Okay. And here, if you're doing classification, you'd put a sign. If you're doing regression, you just output g of x. And if you're doing logistic regression, you output the sigmoid on that. Okay,